Welcome to Module 4, Introduction to Machine Learning. In this module, we begin moving from the general idea of artificial intelligence into one of the main technical approaches that has made modern AI so powerful. Machine learning is the field that allows a system to use data as the basis for improvement, rather than depending only on rules that a programmer has written by hand. That shift is important because many real-world problems are too complex, too variable, or too large to solve with fixed instructions alone. Instead of trying to describe every possible situation in advance, we give the system data, define what success looks like, and allow the model to discover patterns that can support prediction, classification, recognition, or decision making. At a graduate level, it's important to understand machine learning as more than a collection of algorithms. Machine learning is a way of thinking about how knowledge can be represented statistically, how uncertainty can be managed, and how systems can adapt when they encounter new information. A model does not learn in the human sense of having intentions or awareness, but it can adjust internal parameters so that its outputs become better, aligned with patterns found in data. That distinction matters because it helps us avoid both exaggerating and underestimating what these systems can do. When we say that a machine learning system learns, we are talking about mathematical adjustment, performance improvement, and pattern sensitivity, not consciousness or understanding in the human sense. This module will help us build that foundation carefully. We will look at how machine learning enables AI systems to identify patterns from data, and we will connect that idea to the basic learning approaches used across the field. Supervised learning, unsupervised learning, and reinforcement learning are not just vocabulary terms. They represent different ways of organizing a learning problem. In supervised learning, the model learns from examples that already include correct answers. In unsupervised learning, the model looks for structure without being given a labeled target. In reinforcement learning, the model improves through interaction, feedback, and consequences. Each approach reflects a different relationship between data, feedback, and the behavior we want the system to develop. As we move through the module, we will also pay close attention to training data, because training data is not a neutral background ingredient. It shapes what the model can recognize, what it ignores, where it performs well, and where it may fail. A model trained on narrow, incomplete, outdated, or biased data can still produce confident outputs. But confidence is not the same as correctness. This is one of the reasons machine learning requires both technical evaluation and critical judgment. We need to ask whether the data is sufficient, whether it represents the problem responsibly, whether the model generalizes beyond the examples it has seen, and whether the resulting predictions are appropriate for the context in which they will be used. We will also consider why machine learning appears in so many industries. Healthcare uses machine learning to support detection, risk prediction, and treatment planning. Finance uses it to identify fraud, estimate credit risk, and recognize market patterns. Cybersecurity uses it to detect suspicious behavior, classify threats, and respond to unusual network activity. Transportation and marketing use machine learning in very different ways, but both rely on the same broad capability, turning large amounts of data into patterns that can guide action. These examples show why machine learning is not a niche topic. It has become a core part of how organizations automate analysis, personalize services, and make faster decisions under uncertainty. That reaches exactly why the concepts in this module need to be understood with precision, not just familiarity. At the same time, this module will keep returning to limitations and risks because responsible AI begins with understanding the boundaries of data-driven systems. Machine learning models can be useful, but they are not magic, and they are not automatically fair, accurate, or reliable. They can reproduce bias, fail on unfamiliar cases, overfit to training data, or perform well in testing while behaving poorly in deployment. The goal of this module is therefore not only to introduce the major concepts of machine learning, but to help you develop the judgment needed to evaluate when machine learning is appropriate, how it should be trained, and what kinds of evidence are needed before we trust its outputs in real settings. By the end of this module, you should be able to speak about machine learning with both technical clarity and professional caution, which is exactly the balance required for building AI-enabled systems responsibly. In this slide, we begin with the central idea behind machine learning. An AI system can improve its behavior by learning patterns from data instead of relying only on explicit programming. Traditional programming works well when the rules are clear, stable, and easy to describe. If a system needs to calculate sales tax or sort a list of names, a developer can write exact instructions and the computer can follow them reliably. But many intelligent tasks do not work that way. Recognizing a suspicious transaction, identifying a tumor pattern in an image, or predicting traffic congestion all involve uncertainty and patterns that are difficult to capture in simple hand-coded rules. Machine learning becomes powerful because it gives the system a way to use examples from the world as evidence for how future cases should be handled. When we say that a machine learning model learns from data, we are not saying that it understands the world the way a person does. The model is not reflecting on meaning, forming intentions, or developing human judgment. Instead, it is adjusting a mathematical structure so that its outputs become more closely aligned with the relationships found in training data. The data contains examples, measurements, categories, outcomes, or behaviors, and the model searches for regularities inside that information. Those regularities may be simple, such as a linear relationship between two variables, or highly complex, such as patterns across image pixels or language tokens. The important point is that the model's behavior emerges from the data it has processed, not from a programmer writing every possible decision rule in advance. This is why statistical pattern recognition is at the heart of machine learning. A model looks for relationships that appear often enough, strongly enough, or consistently enough to be useful. In a supervised learning problem, the model may learn that certain input features tend to correspond with a particular label or outcome. In other settings, it may discover clusters, similarities, anomalies, or sequences that reveal structure in the data. The word statistical is important here because machine learning usually deals with probability rather than certainty. The model is not producing truth in an absolute sense. It is producing an estimate based on patterns it has learned. That estimate can be useful, but it must always be interpreted as a data-driven prediction rather than a guarantee. The slide also notes that machine learning models can improve performance over time, and this idea should be understood carefully. During training, the model receives data and adjusts itself so that it performs better on the task it has been given. In many systems, improvement means reducing error, increasing accuracy, identifying relevant patterns, or making predictions that better match known outcomes. In deployment, some models may also be retrained as new data becomes available, which allows the system to stay current as conditions change. However, improvement is not automatic, simply because more data exists. The new data must be relevant, reliable, and appropriate for the problem, or the model can learn the wrong lessons and become less useful. Another major purpose of machine learning is generating predictions on new data. Once a model has learned from past examples, we use it to make an informed output for a case it has not seen before. That may mean predicting a number, assigning a category, ranking options, detecting an anomaly, or recommending an action. The phrase new data is essential because the real test of a machine learning model is not whether it can memorize the training examples. The real test is whether it can generalize, meaning whether it can apply what it learned to future cases that are similar but not identical. A model that performs well only on the data it has already seen is not truly useful for decision making. This is why data-driven learning has become central to modern AI applications. Many contemporary AI systems depend on large amounts of data because data gives the model the raw material from which patterns can be discovered. Search engines, recommendation systems, fraud detection tools, speech recognition platforms, image classifiers, and decision support systems all rely on this basic principle. They use data to tune behavior, improve outputs, and respond to situations that would be impossible to fully anticipate through manual rules alone. At the same time, this dependence on data also creates responsibility. If the data is incomplete, biased, or poorly matched to the real-world task, the model's predictions can become misleading. So the lesson from this slide is that machine learning enables AI systems to move from fixed instruction following toward adaptive pattern-based performance. But the value of that performance depends heavily on the data, the training process, and the care with which we evaluate the model's behavior. For this slide, we're comparing the three major learning approaches that organize much of machine learning: supervised learning, unsupervised learning, and reinforcement learning. These categories matter because they help us understand what kind of information the system receives, what kind of feedback guides the learning process, and what kind of problem the model is designed to solve. Machine learning is not one single method applied in the same way to every task. It is a family of approaches, and each approach makes different assumptions about the data, the goal, and the relationship between the system and its environment. Once we understand those differences, it becomes easier to choose the right learning strategy for an AI-enabled application. Supervised learning is often the easiest starting point because the model learns from examples that already include the answer we want it to produce. The training data contains inputs and labels, or inputs and known outcomes, and the model tries to learn the relationship between them. If we train a model to classify email as spam or not spam, the model studies past emails that have already been labeled. In both cases, the model is being supervised because it has a target to compare against. During training, the system measures how far its prediction is from the correct output, and that error becomes the basis for adjustment. This makes supervised learning useful when an organization has historical data with reliable outcomes. The model can be trained to classify, predict, estimate, or rank new cases based on patterns found in the labeled examples. But labels can also be expensive, inconsistent, incomplete, or biased. If the training labels are wrong, the model may learn those mistakes. So supervised learning is powerful, but it depends heavily on the quality of the examples and the answers provided during training. Unsupervised learning works differently because the model is not given a correct answer in advance. Instead, it looks for structure within the data itself. The system may group similar records together, detect unusual cases, reduce complexity, or discover patterns that were not obvious before analysis. This type of learning is useful when we do not yet know the categories, when labeling data would be impractical, or when the goal is exploration rather than direct prediction. In each case, the model helps reveal organization within the data without being told exactly what answer to find. The challenge with unsupervised learning is interpretation. Because there is no labeled answer, the model can identify patterns, but people still have to decide whether those patterns are meaningful, useful, or appropriate. A cluster of customers may reflect a valuable market segment, but it may also reflect noise, missing data, or an artifact of how the dataset was collected. An anomaly may represent a real threat, but it may also represent a harmless unusual event. This means unsupervised learning often requires careful human judgment. After the model has produced its output, the model can surface structure, but the professional using the model must connect that structure back to context, purpose, and evidence. Reinforcement learning introduces a third kind of learning process. Here, the system learns through interaction, rather than simply studying a fixed dataset of examples. An agent takes actions in an environment, receives feedback in the form of rewards or penalties, and gradually learns which actions tend to produce better results over time. This approach is especially relevant when decisions unfold sequentially, meaning one choice affects the next situation the system encounters. Reinforcement learning has been used in robotics, game playing, resource management, and control systems because these problems require a model to learn from consequences. The system is not just predicting an answer, it is learning a strategy for action. What separates these three approaches is therefore not only the algorithm, but the learning relationship. Supervised learning depends on labeled examples and known targets. Unsupervised learning depends on discovering structure without predefined labels. Reinforcement learning depends on feedback from action and consequence. Choosing among them requires asking what data is available, what outcome is needed, and how learning will be evaluated. If we have labeled historical cases, supervised learning may be appropriate. If we need to explore hidden patterns, unsupervised learning may be the better starting point. If the system must improve through interaction over time, reinforcement learning may be the right framework. The responsibility is to match the learning approach to the problem, rather than forcing every problem into the same category. This matters because the wrong learning approach can make a strong data set look weak, while the right approach can turn the same data into useful evidence. This slide focuses on one of the most important ideas in machine learning. Training data shapes model behavior. A model does not begin with an independent understanding of reality. It learns from the examples, measurements, labels, and patterns provided during training. Because of that, the data is not a technical input sitting behind the model. It becomes part of the model's behavior. The model's predictions, strengths, weaknesses, and many failures are connected to the information it was trained on. So when we analyze a machine learning system, we cannot look only at the algorithm. We also have to ask what data taught the model how to act. Training data influences prediction quality because it defines the evidence available to the model. If the data captures the problem clearly, consistently, and with enough variety, the model has a better chance of learning relationships that will carry over to new cases. But if the data is messy, incomplete, mislabeled, outdated, or unrepresentative, the model may learn patterns that are weak or misleading. This is why data quality is so central. Quality includes accuracy, consistency, relevance, completeness, and appropriate labeling. A dataset can be large and still be poor if the information inside it does not reflect the real-world task. More data does not automatically mean better learning. Data quantity also matters, but it matters in connection with complexity. A simple problem may require fewer examples because the pattern is easier to detect. A more complex problem, especially one involving many variables or subtle differences, usually requires much more data. The more complex the task, the more examples the model may need in order to separate meaningful patterns from random variation. However, quantity alone cannot solve everything. A huge data set with repeated errors, narrow coverage, or hidden bias can make the model appear powerful, while reinforcing the same weaknesses at scale. The characteristics of the training data are just as important as its quality and quantity. By characteristics, we mean the distribution, diversity, balance, and context of the examples. If certain groups, situations, or outcomes are overrepresented, the model may become better at handling those cases and worse at handling others. If rare but important events are missing, the model may fail precisely when the system is needed most. This matters in healthcare, finance, hiring, and cybersecurity, where errors can have serious consequences. A model trained mainly on one population, one environment, or one historical period may not generalize well to another. The model may seem accurate in testing, but only because the test conditions are too similar to the training conditions. This leads us to the idea of generalization. A useful machine learning model should not merely memorize the training data. It should learn patterns that remain valid when new data arrives. If a model performs well on training examples, but poorly on new cases, it may be overfitting. Overfitting means the model has learned the details of the training dataset too closely, including noise or accidental patterns, instead of learning relationships that truly apply beyond that dataset. A model may also underfit if it is too simple, or if the data does not give it enough information to capture the underlying relationship. Both problems show why training data and model behavior have to be evaluated together. Training data can improve performance because better examples help the model recognize stronger and more useful patterns. When the data is representative, carefully prepared, and connected to the task, the model is more likely to produce reliable predictions. Good training data can reduce error, improve fairness, and increase confidence in the system's ability to work outside the training environment. But the same training process can also introduce limitations and risks. If past decisions were biased, the model can learn that bias. If historical records leave out certain populations, the model can ignore those populations. If the data reflects conditions that have changed, the model can become outdated even if it was once accurate. This is why analyzing training data is a professional responsibility, not just a technical step. Before trusting a machine learning model, we need to examine where the data came from, how it was collected, what it includes, what it leaves out, how labels were created, and whether the dataset represents the deployment context. We also need to test performance across different conditions, not just report a single overall accuracy number. A model can look strong on average while performing poorly for important subgroups or unusual cases. The core lesson is that training data is one of the main forces shaping model behavior. It can make machine learning useful, but it can also create blind spots, unfair outcomes, and fragile predictions if it is not handled carefully. Once a model can recognize patterns, generate predictions, and support decisions, the capability can be applied across many industries. Organizations collect data from operations, customers, transactions, sensors, records, or digital activity, and machine learning helps convert that data into usable insight. That is why machine learning has become a common layer inside modern AI systems. In healthcare, machine learning is often used to support recognition and prediction in settings where complex information must be interpreted carefully. A model might help identify patterns in medical images, estimate the likelihood of a patient developing a condition, or flag cases that require closer review. The value is not that the machine replaces clinical judgment, because healthcare decisions involve ethics, context, and human responsibility. The value is that machine learning can surface patterns that may be difficult to detect quickly across thousands or millions of records. When used responsibly, it can help professionals prioritize attention, and make better informed assessments. Finance provides another strong example because financial systems generate enormous volumes of structured data. Banks, lenders, insurers, and payment processors use machine learning to detect fraud, estimate risk, classify transactions, and identify unusual activity. In fraud detection, the model looks for patterns that differ from normal behavior. A transaction may not be clearly fraudulent by itself, but it may become suspicious when compared with a person's usual spending patterns, location, timing, device, or transaction history. This shows how machine learning supports prediction through context, because the model learns relationships among many signals. Cybersecurity also depends heavily on pattern recognition, because threats often appear as changes in behavior. A machine learning system can help identify unusual login attempts, suspicious network traffic, malware-like behavior, phishing patterns, or activity that deviates from a normal baseline. This is useful because attackers constantly change tactics, and fixed rules may miss new variations. However, a model can also produce false alarms or miss attacks that do not resemble the training data. For that reason, it works best alongside expert analysis, layered controls, and ongoing monitoring. In transportation, machine learning supports systems that need to interpret changing conditions and make predictions in dynamic environments. Traffic forecasting, route optimization, logistics planning, fleet management, and driver assistance technologies all depend on data about movement, timing, location, demand, and risk. A model might predict congestion before it becomes severe, recommend a more efficient route, or help schedule deliveries based on expected delays. In more advanced systems, it can also help interpret sensor data, though those applications require rigorous testing because errors can affect physical safety. Marketing uses machine learning in a different but very visible way. Organizations use it to understand customer behavior, segment audiences, recommend products, personalize messages, and predict which customers are most likely to respond to a campaign. A recommendation system learns from previous behavior and compares it with patterns across many other users or products. The goal is to present information that is more relevant to the individual, but this also raises questions about privacy, manipulation, and over-personalization. Across all of these industries, the common thread is that machine learning supports pattern recognition, prediction, and intelligent decision making. Pattern recognition helps the system notice regularities, similarities, anomalies, or relationships in data. Prediction helps the system estimate what is likely to happen next, or what category a new case may belong to. Intelligent decision making does not mean the machine has human wisdom. It means the system can provide outputs that help people or organizations choose actions based on learned evidence. So when we evaluate machine learning applications across industries, we should avoid treating them as isolated examples. Healthcare, finance, cybersecurity, transportation, and marketing are different fields, but they all show the same broader principle. Machine learning becomes valuable when a problem contains relevant data, pattern structure, and a meaningful decision that can be improved by prediction or classification. A model that is acceptable for recommending a product may not be acceptable for diagnosing a condition or flagging a person as a security risk. The central lesson is that machine learning is widely applicable, but responsible application depends on matching the model to the industry context and the consequences of being wrong. This slide brings the module to a responsible close by focusing on the limitations and risks associated with data-driven AI systems. We have emphasized what machine learning can do. It can identify patterns, improve performance, generate predictions, and support decision-making across industries. But those capabilities depend on a very important condition. The model can only learn from the data it receives, and that means its behavior is shaped by the quality, history, and limits of that data. A machine learning system may appear objective because it produces numerical outputs, but those outputs still reflect human choices about what data to collect, how to label it, which features to include, and how the model will be evaluated. This dependence on training data is one of the main reasons machine learning systems can produce biased results. Bias can enter the system in several ways. It may come from historical patterns that reflect unfair treatment, data sets that underrepresent certain groups, labels created through inconsistent human judgment, or measurements that do not capture the full complexity of the real-world situation. If a model learns from biased data, it can reproduce those patterns in its predictions, even when no one explicitly programmed the model to discriminate. This is why bias in machine learning is not always obvious at the surface level. It may appear as unequal error rates, lower accuracy for particular populations, or decisions that seem statistically justified but produce unfair outcomes in context. Poor generalization is another major limitation. A model may perform well on the data used during development, but fail when it encounters new cases that differ from the training environment. This happens because the model may have learned relationships specific to the original dataset rather than relationships that remain stable in the real world. Generalization is what separates a useful model from a model that only looks impressive in a controlled setting. If a healthcare model is trained on data from one hospital system, it may not perform the same way in another hospital with different patients, equipment, or workflows. If a cybersecurity model is trained on yesterday's attack patterns, it may struggle with tomorrow's techniques. So the question is not only whether the model learned, but whether what it learned transfers responsibly to the context where it will be used. The slide also highlights dependence on training data quality, and this connects directly to data-driven learning. Machine learning does not fix poor data automatically. If the data contains errors, missing values, outdated information, inconsistent labels, or irrelevant features, the model can absorb those weaknesses. Sometimes it may even amplify them, because the model processes patterns at scale. A small labeling problem can become thousands of flawed predictions after deployment. A narrow data set can become a system that performs confidently, but only for cases it has seen before. This is why data, preparation and validation, testing, and monitoring are central to whether the model is safe, useful, and trustworthy. Another risk is that machine learning outputs can create a false sense of certainty. Because models often produce scores, probabilities, classifications, or rankings, users may treat those outputs as more precise than they really are. A prediction is not the same as a fact. It is an estimate based on learned patterns, and every estimate has uncertainty. In higher stakes settings such as healthcare, finance, education, or security, the consequences of error can be serious. Responsible use requires asking what happens when the model is wrong, who is affected, and whether there is human review. These limitations do not mean that machine learning should be avoided. They mean that machine learning must be evaluated with professional care. A responsible AI application should be tested on data that reflects the deployment environment, monitored after release, and reviewed for uneven performance across relevant groups or conditions. It should also be designed with clear boundaries so users understand what the model can and cannot support. A model may be useful for recommending further review, but inappropriate as the sole basis for a final decision. That distinction matters because model outputs may influence people who never see the system directly. The essential lesson from this slide is that data-driven AI systems are powerful because they learn from data, But that same dependence creates risk, bias, poor generalization, and weak training data quality determine whether a system performs responsibly in the real world. Understanding these limitations helps us move beyond enthusiasm and toward professional judgment. We should recognize when a machine learning model is useful, but we should also question the evidence behind it, the data that shaped it, and the consequences of trusting it.